Good day, everyone. Welcome to our discussion for today. So we'll discuss now the rectangular coordinates. So this is the continuation of our last video, the rectilinear motion, and this time we are going to deal with the curvilinear motion. So rectangular coordinate system is very important in dealing problems with um, curvilinear motion. Okay, so rectangular coordinates or the x and y coordinates. This system of coordinates is particularly useful for describing motions where x and y components of acceleration are independently generated or determined. The resulting curvilinear motion is then obtained by a vector combination of the x and y components of the position vector, the velocity, and the acceleration. So here we have the vector representation, but before we go to the details of this one, let's try to just quickly see or review what's this vector is all about. Okay, so when we speak of vector, so the term vector is used by scientists to indicate a quantity such as displacement or velocity or force that has both magnitude and direction. A vector is often represented by an arrow, no, something like this. So this is an example of vector. We have here the initial point, okay, and this is what we call the terminal point. So we have here the vector AB. All right. So a vector is often represented by an arrow or a directed line segment. So the length of the arrow represent the magnitude of the vector, and the arrow points in the direction of the vector. All right, so we have here some concepts like equivalent vectors. So what does it mean by equivalent vectors? So they're equivalent if they have the same length and direction. Okay, so that's equivalent vectors. So these are the examples. Okay, so they're just equivalent vectors. Then we have vectors in standard position. Okay, so we have some example here, but we don't bother to solve this one. We'll reserve our solution in our next examples. We have here the vector notation. So we have the two-dimensional vectors, we have the three-dimensional vectors. So I think we have to focus on this part here. And magnitude of vector. So these are the calculation. When you calculate the magnitude of vector, so we have here the magnitude of vector v, just the square root of. So vector 1 squared plus vector 2 squared plus vector 3 squared. Or this is equivalent to the square root of, okay, this one the square root of, no, the square of the sum. Sorry, the sum of the squares of the three vectors in this case. And this is equivalent to the square root of the difference of these x coordinates square plus the square of the difference of the y coordinates plus the the square of the difference of the z coordinates. All right, so we have also operation of vectors. So these are the addition. Okay, this is how to add vectors. We have the scalar multiplication. So we have k times u equal to k times u sub 1, k u sub 2, and so on and so forth. And this is enclosed by this symbol. Then in addition to vectors, we have head to tail. Okay, so we have something like this. We have vector u, vector v. All right, so we have here v1, v2. These are the x component. We have the y component of v. All right, and to sum up u and v, so we have here the vector sum, and this is represented by this one. So u1 plus v1, I mean the coordinates, coordinates of this one is u1 v1, u2 v2. Okay, so I hope you can also add vectors using the parallelogram method. So you have this vector, you vector u, vector v, and then you have to form this parallelogram, and then you connect these two lines meets at this point, and then you draw the diagonal, and you have here the sum. So this is the parallelogram method. Okay, so we have addition of vectors, positive, negative values. So these are the illustration, and we have here the properties of vector operations. All right, so you just review this. You may be using this one in solving problems, rectangular coordinates or curvilinear motions. Okay, so we have here some examples. So you just explore them also. This is not the main topic, we're just reviewing class. And one of the important thing here is the term unit vector. So what does it mean, unit vector? So vector v of length 1 is called unit vector. So we'll be mentioning this concept here in our main discussions. So the standard unit vectors are, we have I, 1, 0, 0. So we have the x, y, z. Then we have for g, you see here, only this part is 1, the x part, then the rest is 0. Here, the y part, so for j, and here for the key part, that is only 1. And then we have here some examples. So a vector v or any vector v represented by this one can be written as a linear combination of standard unit vector as follows. Okay, and finally we have these um, vectors represented by this expression. Okay, and then we have here the other properties. We have the sample sample calculations here. Okay, I want you to explore also to help you. And we have some examples here on how to calculate the magnitude. And in this case, after the calculation, you can see here, this is what we call the length or the speed, this part here, and what is inside the quantity that contains I and j. So this indicates direction of motion. All right, so I think this is the brief of about vectors, and now we'll go back to our main topic. Okay, so vector representation, the particle path of figure 2 slash 5. So if you read the readings that I have given you in the BBL, so this means you will see this one. But anyway, I will show this figure here. Right, so this is the illustration that is in figure 2 slash 5. So we have here the path of the particle, the color which is orange. Okay, it's also show again in figure 2 slash 7. So this is the new figure, this one. So we have here the vector r, all right, and we know that the velocity is always tangent to the path. So this is the path. So this is the velocity. All right. So the particle path of figure 2.5, which is this one, and shown again here in this illustration, along with x and y axis. So the position vector r. So this is the position vector, as mentioned in our very brief review. So the position vector r, the velocity v. So this is our velocity v, and the acceleration a. All right. So we have here the acceleration a. Particle as developed, no, as explained in the reading materials, the Wiley plus. So are represented in figure 2 slash 7 together with their x and y components. So this is now the summary. All right. So with the aid of the unit vectors I and j, we can write the vectors r. Okay, so since we use only the x and y coordinate here, rectangular coordinate x and y. So we can we can write the vector r, so in terms of the unit vectors. Okay, it is written as r equal to x sub I, x I plus y j. Okay, so this is the x component, this is the y component, and a in terms of their x and y components as well, something like this. Thus, this one can be represented as, if the vector is represented by r equal to x I and yj plus yj, then we know that v is the velocity. So if this is the force or the vector, the that indicates the displacement. We have this r, the length of this one r. So if you take the derivative of this, it will give us the the velocity. So it's just like this is our s, no? In our previous discussion in our rectilinear motion, you think of it as our s, the displacement of the position. Okay, then v here is the velocity, which is the derivative of this. So we have v equal to r dot. So at the head of the r we have dot, means derivative of this. So it gives us x dot I plus y dot j. So this is our velocity. And now for the acceleration, we know that acceleration is just the derivative of the velocity. If you can still remember in our previous discussion, we have uh, in our previous discussion we have s. So when you take the derivative of s, in our discussion we use s dot, no, s dot. So this is equal to v, right? S dot is equal to v, meaning derivative of s. But in this case we discuss about r. Okay, so here we use r here, or vector r. So this is our vector r. So now when you take the derivative of r, sorry, I will okay, so when you take the derivative of r, so we put that here to indicate that the derivative of r. So this is our v. Okay, this is the velocity. And as we discussed before, we have, if you take the derivative again, for the second times derivative of s, so you have s double dot. So this indicates our acceleration. Or similarly, for this case, if you take the derivative of r once again, so r, sorry, this is r, so r double dot. So meaning if you take the derivative of then of this again, so this would be our acceleration. This would be our acceleration, which is equivalent to just the derivative of v. Take the derivative of this one, which is equal to r dot. So derivative of the velocity, just one. Sorry, only one dot here. Okay, so this is what is talking about here. So we have here the velocity equal to r dot, and that is equal to x dot I plus y dot j. Or for our acceleration, which is v dot or equal to r double dot equal to x double dot I plus y double dot j. Okay, so as we differentiate with respect to time, we observe that the time derivatives of the unit vector are zero. So the reason is that their magnitudes and directions remain constant. So that's why it becomes zero. Okay, so the scalar values of components of v and a are merely this: v sub x equal to x bar and v sub y equal to y bar, and our ax is, or a sub x equal to v sub x dot, sorry class, I use dot instead of bar, no? V sub x is equal to x dot, meaning derivative of x, and v sub y equal to y dot, meaning derivative of y, and a sub x equal to v sub x dot, which is equal to x double dot, and a sub y is equal to v sub y dot equal to y double dot. So in other words, class, the when you speak of velocity, no, the x component of the velocity is just the derivative of this x, and for y, the y component of the velocity is the y dot, or derivative of this y, and the acceleration is just the derivative of velocity, or the second the derivative, no? We take the derivative of x twice, and so with the acceleration, the y component of the acceleration. Okay, and here it is the representation of all this thing here. Okay, so we have here the with reference with the aid of the unit vector. So we have here the I component, the x component, the y component. So x component is presented by I, the y component is j. All right, so we have here the position vector r. All right, and with respect to this path of the movement of the curve of the particle, so with reference to that, we have this velocity which is tangent, no? Tangent to the path of the particle. So velocity is just tangent. Okay, so we have this velocity as tangent to this, and then you draw the horizontal component, or the x component, and the y component of the velocity. All right, now for the acceleration. So acceleration is just something like this. Okay, so it's going opposite, no? Uh, in opposite direction. So this is the acceleration here. This is the y component, and sorry, the x component, and this is the y component. Okay, so we will use this concept, class, in solving some example. We have just one example, and then I will cut the video and make another video for the next example, so that it will not be very long. Okay, so as observed previously, so the direction of the velocity is always tangent to the path, no? As I've mentioned a while ago. And from the figure, it is clear that, no, from this figure here, if you talk about velocity, so we have here v squared equal to, just by using Pythagorean theorem. So v here is the hypotenuse. We have here the base of the triangle, and this one here is just equal to vy. They're just parallel. So using the Pythagorean theorem, we have v squared equal to the sum of the squares of this x and y components of the velocity. And we can solve from this equation, we can solve for the velocity. So taking square root on both sides, so we have v equal to the square root of v sub x squared plus v sub y squared. And we have here the angle theta. So tangent of that is equal to opposite. Our opposite is vy. So this component here, this side of the triangle, is just the same as this. So this is also vy. So when you seek a tangent, no, tuwa, no, from our code tuwa, suka tuwa. Okay? Tangent opposite over adjacent. So tangent of this angle theta is opposite, meaning this side here, which is equal to this one over adjacent. So this is Vx, this is Vy. So we have Vy over Vx. And for this part here, for the acceleration, so again, using the Pythagorean theorem, so A here, the acceleration, this is the hypotenuse of this triangle here. Okay, so using Pythagorean theorem, you have A squared equal to the square of this component, A sub x squared, plus this one here, which is equal to this, meaning this part here of the triangle is equal to this one, ay. So you square that also, so you sum up, and to solve for a is the square root of a sub x squared plus a sub y squared. Okay, so if the angle is measured counterclockwise, so what does it mean counterclockwise? So the clock turns to the right. When you speak of counterclockwise, means it goes in this direction, so this counterclockwise. So if the angle is measured counterclockwise from the x-axis to v, meaning from here to v, something like this, for the configuration of axis shown, then we can also observe that the derivative of y with respect to x, meaning the dy over dx, is equal to tangent. So remember this concept, class, from our from our calculus, differential calculus. So derivative, the derivative of y with respect to x is just equal to, so from this illustration here, so this is just equivalent to tangent. So remember, this is the slope, right? This is tangent of theta, which is equivalent to, so from the picture, this is equivalent to vy, v sub y divided by v sub x. Okay, so if the coordinates x and y are known independently as a function of time, x equal to f sub 1 of t and y equal to f sub 2 of t, then for any value of time, we can combine them to obtain r. And similarly, we combine their first derivative x dot and y dot to obtain the v, and their second derivative as well, x double dot and y double dot, to obtain the acceleration a. So on the other hand, if the acceleration components a sub x and a sub y are given as a function of the time, we can integrate each one separately with respect to time. So so with respect to time, once to obtain Vx and Vy, and again to obtain x equal to f sub 1 of t and y equal to f sub 2 of t. Then elimination of the time t between these two parametric equations gives the equation of the curve path that is expressed in this form, y equal to function of x. So it is purely y as a function of x. So from the foregoing discussion, we can see that the rectangular coordinates or coordinate representation of curvilinear motion is merely the superposition of the components of two simultaneous rectilinear motion in the x and y directions. Therefore, everything covered in Article 2 on rectilinear motion can be applied separately to the x motion and the y motion. So that's why, class, before we discuss this one, we had a video that was videos, no, video lessons, just to review what we had discussed on rectilinear motion, because the concepts that was discussed there, the concepts that were discussed there, will be used in this topic. Okay, now we have what we call projectile motion. So projectile motion is an important application, no, of the two-dimensional kinematic theory. An important application of two-dimensional kinematic theory is the problem of projectile motion. So the first treatment of the subject, we neglect the aerodynamic drag and the curvature and rotation of the Earth, and we assume that the altitude change is small enough so that the acceleration due to gravity can be considered constant. So we have to use these assumptions in order to solve some problem class that's not so sensitive of those factors that mentioned above. So with these assumptions, rectangular coordinates are useful for the trajectory analysis. Now for the axis shown in figure 2/8, no, from here, from this picture here. So the acceleration components are given in this. So actually this is just taken from here, class. So when you differentiate it further, take another derivative of this. When you take the derivative of this, it will give us this one. Okay, so the acceleration at the x component is equal to 0. And for the vertical component, this is the horizontal component, this is a vertical component. It's just the negative of the uh, gravitational acceleration. So integration of this acceleration follows the results obtained previously in article 2/2, the A for constant accelerations, and yields this. Okay, so if you cannot recall, so I'll help you recall on that. Okay, so last time we have, I'm just looking for the arrow. Okay, so if you can still remember, if you cannot recall quickly, so here's the two the formula mentioned. No? Those formulas were derived from this concept class. Okay, so if the acceleration is not constant, so we have this general formula that we need to use. Okay, so that was taken from that derivation. So we have here v sub x equal to, so from this illustration here, our v sub x, meaning the horizontal component of this uh, projectile motion for this projectile is the v sub x. Well, in this case, this is represented by v sub x sub 0. So meaning this is our horizontal component. So that's why we have here the vx, because if you look at our previous illustration, so we have here vx. We have the vx here. Okay, from this is the horizontal component, this is the vertical component. So vx is the horizontal component. So in our illustration here, so this is represented as v sub x sub 0. Okay, and then where do you get this one? So you just take this triangle here. um, so we have a triangle that's formed. Okay, so this is our v sub 0. This is the horizontal part, added the hypotenuse. Sorry. Oh, it's very hard to draw a straight line here. Okay, anyway, I'll just use this illustration here, class. Here, just consider this triangle. Okay, now we have this. To solve this component, the horizontal part of this triangle, you have to use cosine. No? we have cosine of the angle. So the angle here theta. So what is the so from our trigo we have cosine sukatwa. Sukatwa means cosine ka. Okay. So for cosine means you have the adjacent. You have the adjacent over hypotenuse. So the adjacent is this one, which is our adjacent over hypotenuse. So cosine, that is v, you know that is vx, right? And over the hypotenuse, which is v sub 0. So solving for, sorry, this is vx. Okay, v sub 0. Okay, so solving for vx, so our vx here is equal to v sub 0 cosine of theta. Okay, where our v sub x, so our v sub x is equal to this one. So that's why you have here this component as v sub x sub 0 is equal to v uh, sub 0 cosine of theta. Okay, so you have here, then from here, if you take the derivative this one, so this is equal to 0, derivative of this one, so this is constant, so derivative constant is equal to 0, so that's why you have acceleration, the component acceleration is equal to 0, and for the this is for the horizontal component. For the vertical component, so we have here this equation. Okay, we have this as a constant, so take the derivative of constant is 0, so take derivative this with respect to time, so you have negative g. Okay, so that's the acceleration. And using the other derivation, so we have this v squared y, or v sub y squared, equal to v sub y sub 0 squared minus 2g times y minus y sub 0. Okay, so these are the important formulas that we need to use. So in all these expressions, the subscript 0 denotes initial conditions, frequently taken as those at launch, where for the case illustrated, x sub 0 equal to y sub 0 equal to 0. So note that the quantity g is taken to be positive throughout this text. Okay, so that's the concept class, basic concept for the projectile motion. Okay, now we can see that the x and y motions are independent for the simple projectile. No, you see here, so they are independent under consideration. So elimination of the time t between x and y, x and y displacement equations show that path to be parabolic. Okay, so if we were to introduce a drag force which depends on the speed squared, for example, then the x and y motions would be coupled or interdependent, and the trajectory would be non-parabolic. So when the projectile motion involves large velocities and high altitudes, to obtain accurate results, we must account for the shape of the projectile, the variation of g with altitude, the variation of the air density with the altitude, and the rotation of the Earth. So these factors introduce considerable complexity into the motion equations. And numerical integration of the acceleration equation is usually necessary to deal with this kind of situation. So this is an example of a stroboscopic photograph of a bouncing ping pong ball. Suggests not only the parabolic nature of the path, but also the fact that the speed is lower near the apex. Fact that the speed is lower near the apex. So this is the apex. So you see the speed here is lower, right? But as you see, as the ball, the height of the ball, the altitude of the ball that is bouncing is lower and lower, then you can see that the velocity or the speed becomes faster, right? So if it's near the apex, like this one, near the apex, so the speed is slower, but when, as you see here, meaning here, you can see that the speed here is faster. Okay, so those are the concepts, class, and hope for this example we'll be able to solve this using those concepts discussed. But I think before we solve this, I'll end this discussion as mentioned in the beginning after this problem, because if we go on and on, then it would be too long, so it's very hard to upload the video. Alright, so this is the problem, class. The curvilinear motion of a particle is defined by Vx equal to 50 minus 16t and y equal to 100 minus 4t squared, where v sub x is in meters per second, y is in meters, and t is in seconds. It is also known that x equal to 0 when t is equal to 0. So plot the path of the particle and determine its velocity and acceleration when the position y equal to 0 is reached. Okay, so this is our solution. So the x coordinate is obtained by integrating the expression for Vx using the concept that we have discussed earlier. And the x component of the acceleration is obtained by differentiating v sub x. Thus, we have this now from the concept that we have discussed a while ago. We have dx equal to, because we know that no, from the concept v sub x is just to have a quick review. So we have v sub x, so this is just the derivative of x with respect to time. Okay, and then you cross multiply, so we have v sub x dt equal to dx. Okay, and then you just interchange the position, so dx equal to vx dt, and then you integrate both sides. So integrating both sides, okay, so integrating both sides, so this is it. And we have the limit from 0 to x, no, for this part here. And vx is given. Vx is given here. So this is given. Okay, then substituting vx here and then do the integration. So we got x here with the limit 0 to x. So you can calculate for x here. So this is the resulting equation for x. Okay, after integration. Then we know that this is our vx, right? So when we, and this is our x, we have this relationship that acceleration, because you have vx equal to dx over dt. So when you take the derivative of vx, so you have derivative of vx with respect to time. So this is just the acceleration. Okay, so derivative, derivative vx, or we have v prime, v dot, or we can also write a equal to vx dot, meaning derivative of vx equal to acceleration. So we have here acceleration, or a sub x equal to v sub x dot. So derivative of this v, so our v, we have here v, derivative this, you take derivative of this is our vx, right? Remember, this is our v sub x, so we take the derivative of that, so 50 derivative of, so what will happen? So derivative of, this is our v sub x. So derivative of this, derivative constant is 0. Derivative of 16t, negative 16t is negative 16 meter per second. So we get the acceleration. All right. Now for the y components. Okay, so for the y components of velocity and the acceleration, so as you can see here, we have v sub y equal to y prime, meaning derivative of y. So we're given y here, right? So we're given y here. So take the derivative of this. So we have the vertical component of the velocity. So derivative of y is given. So derivative of this. Okay, so derivative constant is 0. So derivative of this is minus 8 times t, negative meter per second. And we know that the acceleration is just the derivative of this. Take the derivative of this. So what will happen? So derivative of minus 8t with respect to t. So we have minus 8 meters per second. Okay, so that is the y component of the velocity and the acceleration. I'm just writing that one. And we can now calculate the corresponding value of x and y for various values of t and plot x against y to obtain the path as shown. Alright, so from here, this is plotted class. This is our y, this is our x. So we have solved x and y. So we have the y here, and then we solve for, okay, so from here, so we have when y equal to 0, so when y equal to 0, meaning here, when y is equal to 0, so substitute y equal to 0 here, and then calculate for t. So we have substituting y equal to 0 to this equation. So we have y equal to 100, but y is equal to 0. So y equal to 100 minus 40 squared. So from here, we can solve for t. That is 5 seconds. So for this value of the time, so we have substituting, we can solve for v sub x. Okay, because we have time now here, that is 5 seconds. So v sub x equal to 50 minus 16 times t. Our t is 5 seconds, so we got 30 meter per second. Now for v sub y, where's our v sub y? We already calculated v sub y here. Okay, this is our v sub y. Our v sub y here is 8, sorry, negative 8 times t, but t is 5 seconds. So substituting, so we have minus 40 meter per seconds. So we have now the x and y component of the velocity. So therefore, we can now solve for the velocity v. Okay, so from the formula, we have the square root of just the component. You square this one plus the square of this one, then take the square root, so that would be our v, which is equal to 50 meter per second. All right. Now for the acceleration, so how to solve for the acceleration? So we have to make use of to calculate for the acceleration. So how will we solve for the acceleration? We have 16. So where we get the 16? Okay, so from the formula now for the acceleration, if you can remember here, acceleration here. So we have to make use of this. Okay, for the acceleration, we have to make use of this formula. So a equal to the square root of ax squared plus ay squared. So we have to make use of that formula to get the acceleration. Okay, so for the acceleration, square root of ax squared. So our ax, we got the ax already here. We take the, where's our ax? Here. So this is our ax, 16. Okay, and then our ay, which is minus 8. Okay, so using these values, we can calculate for the acceleration. Alright, so we got this 16, our ax, this is our ay. So taking this, you square this one, plus the square of this one, this is our ax, this is our ay. You take square of this, then add, then take the square root, you get this 17.89 meter per second squared. Okay, so that's our example number one. I hope you understood this one, class. And that's not yet the end. We still have this part here. So the velocity and acceleration component and the resultants are shown on the separate diagram for point A. Now, this is our point A, where y is equal to 0. So for this point, y is equal to 0. That's the condition we may write. So we have here the velocity in terms of uh, vector components. So we have, you just take this value here. This is our Vx, right? Vx, which is equal to 30. So negative 30. Then we just put I minus this value here, negative 40 J, then meter per second. So in terms of vectors, so this is our representation. Then the acceleration is just the same. You just take this value here. So minus 16 I minus, because this is minus, that's supposedly plus, but since this is minus, so you take only this part here. So minus 8g meter per seconds. Okay, this is the complete illustrations here. Okay, acceleration 16, this is the result. This is the uh, vertical as horizontal component, this one. Negative, so it means that it's going to the left. Then our ay is negative also, so going down. So therefore our acceleration is in this direction. Okay, it follows this. So particle is going in this direction. And for the Vx, so again Vx, so we take this value, negative 30, so negative, so going to the left. This is also negative, so going down. So this is our velocity. Okay, 50 meter per seconds. So this is the helpful hint, class. Now we observe that the velocity vectors lies along the tangent to the path as it should, but that the acceleration vector is not tangent to the path. So remember the difference, class. Vector or velocity vector is lies along the tangent, tangent to the path. So this is our path, and this vector here, velocity here, is tangent to the path. But the acceleration is not, is not tangent to the path, the acceleration. So take note on this. So note especially that the acceleration vector has a component that points toward the inside of the curved path. And we concluded from our diagram that it is impossible for the acceleration to have a component that points towards the outside of the curve. Okay, so that's all for this problem, and see you again in our second problem. Bye.